Okay. So today we're just going to be reviewing the exam is going to be on Monday, and it's basically going to be sections 2.1 through 2.7, I think is where we stopped, and 3.2. There's really only so many functions we know how to take derivatives of so far. We know how to take derivatives of power functions, so a constant times x to a power. We know how to take derivatives of sums of functions of that type, and then now we know how to take derivatives of basic, exponentials and e to the x. Okay. Now, I just went into the textbook. I just printed off since the bulk of the test is on chapter 2. I just printed off the summary from chapter 2 and then a bunch of review exercises. If you go look on My Math Lab under announcements, you'll see that I've kind of skipped over some problems we didn't focus on in class. So I've got suggested review exercises. So focus your attention there. If you're bored and you need more practice, or you feel you need more practice, I also have extra suggested exercises from each section. Okay. And then 3.2, rather than going to the back and looking at the review, I just went to the back of to the exercises in the section 3.2, and I recommended a bunch of those problems as well. Okay. All right. So let's anybody have really any questions on? First of all, let's just get what to expect on the test out of the way. Anybody have any particular questions? Okay. I can start kind of going over a list of topics we should all know. And then as soon as someone sees something like, hey, I'd like to see one of those, then just raise your hand or throw something at me or call out or get my attention somehow. Okay, so exam topics. Okay, so first bullet, we need to be able to do limits graphically. And analytically or algebraically. And I'm a little bit mixed. I could also say limits numerically, where you have to make a table and let your x value get close to something and you see what the function approaches. Probably won't do that on a test. However, if you struggle to see what method to use to calculate a limit, you can always do the numerical approach. Okay. So, but mainly though, just limits graphically and algebraically. Okay. We'll do determine continuity graphically, and I guess we can do that algebraically as well.
And for that one, do you want us to say which of the three it is?
Yeah. So, I'll ask you, is the function continuous at this point? And you can say yes, because the limit equals the value of the function. Or you can tell me it's not continuous because either the function's not defined, maybe the limit doesn't exist, or in the case the function is defined and the limit exists, if those two values aren't the same, it's not continuous. So, for instance, you could say, I could give you a graphical one. Something like this. And I'll just call this A and this one C. And maybe I'll just make up a third point. I'll just call this B, A, B, and C. And I could just, on the test, I'll give you a specific graph and I'll tell you, the heights at each of these open circles. You'll be able to tell what the value of the function is at that closed circle. But just to give you a sense of what you need to know, make sure you know the continuity checklist. So f is continuous at x equals a if all of the following are true. Okay, and I think, if I give you something like this, I'll be asking you a mixture of limit questions and continuity questions, just so I can take care of those two topics in a single question. So what are the things that have to be true at A? So the first thing is that f is defined at A. And then anybody remember what the second condition for continuity is?
The limit exists.
Okay, the limit as x approaches a of f of x exists. In 3, you have to rectify the first two. The function has to be defined at a, and the limit has to exist, and the value of the function and the limit have to be
Equal.
the same. Right? So 3 would say the limit as x approaches a of f of x has to equal the value of the function there. So if I say, is the function continuous, and I say why or why not, I don't really want you to say because there's a hole there. Okay, I want you to tell me either the function's not defined, the limit doesn't exist, or the limit and the function value are not the same. So for instance, is the function going to be continuous at a? No. So which one of these 3 conditions is violated? Is the function defined at a? Yeah, right? Because at a, there's a point on the graph. So it doesn't violate 1. Does the limit exist at a?
Sure does.
Yep, because if you draw your vertical line, whatever the height of this point is, right, if you approach a from the left or the right, the y coordinates are approaching the same y value, or output. So the limit would exist. But what's the problem at a?
Not equal.
Yeah, so the limit as x approaches a of f of x is not equal to f of a. So f is discontinuous at a. Or you can say it's not continuous, either or. And then what about at b? Is it continuous there? Okay, which rule is being violated this time?
2.
You sure it's
No,
2?
it's 1.
The limit exists again, draw your vertical line. From both sides, the curve is approaching the same value, or the same place.
Don't you lift your pen because it's a hole still?
Yes, intuitively, I'd have to lift my pen, so intuitively I know it's not continuous. But I want an answer based on these 3 conditions. I don't want you to just say, oh, I can't draw it without lifting my pencil.
But it's
I
still a limit, right?
The limit will exist. It'll be, let's call this d. So like up here at a, the limit is d, but the function value's up here at e. Down here, let's say the output, so at b, this open circle is at a height of f. That'll be the limit. But the function's not defined. So number 1 is violated. So because of the open circle, the function's not defined there.
Do we have to memorize like rules in terms of numbers, or can we just say, oh, it's not defined there?
Yeah, you can say the function's not defined there, so it's not continuous. You know, what you're probably going to see, the first question will probably say, find the limit at a. And then the second question will say, what's f of a? And then the third part will say, is it continuous there? Okay. I think there was some questions on the homework similar to that, or even on the quiz that I gave.
It's going to be similar to the quiz that we had.
Yeah, I mean, I'm not going to throw you tons of curveballs here. I mean, if I'm going to put something on a test, I want to make sure that we've either spent time on it or I've assigned it as homework. I'm not just going to randomly throw you things that you haven't seen before. Okay. And then what about at C, though? So there's the value of the function at C. It'd be continuous there, right? It's defined. The limit will exist, and the limit will be the same as whatever the value of the function is. Okay. So that's what I'm looking for when I'm talking about determine continuity graphically. And you should probably be able to explain why it's not continuous using limits on those 3 conditions. I don't want to get too carried away with continuity. It'll most likely just be a graphical continuity question. Okay. So limits graphically and algebraically, continuity graphically and algebraically, but most likely just graphically. How about you should be able to find horizontal asymptotes and vertical asymptotes and verify with limits if asked. So does anybody want to see what I mean by that? Okay. Because to find the horizontal and vertical asymptotes, you can just use algebra and look at the function. Okay, but I might ask you to verify with a limit. So if you wanted, you'd have the definition. So vertical asymptotes, the definition is if the limit as x approaches a from the left of f of x is plus or minus infinity, or the limit as x approaches a from the right of the function is plus or minus infinity, then x equals a is a vertical asymptote. Okay. But there's a theorem that tells you don't want to just, this doesn't really give you a good procedure for telling you what the vertical asymptotes are. Okay, this is just something you use to verify that something is a vertical asymptote. So for instance, let me come up with something. Now, you might actually have to do this factoring on your own. What if I have 2x squared minus 4x plus 1 over x minus 2 times x minus 3? And I say find vertical asymptotes and verify with limits. Okay. So what was the rule algebraically for determining?
Where your denominator equals 0.
Okay, so first of all, you have to look and see where your denominator is 0, but you have to make sure that the top doesn't equal 0 at that value. Okay, so first of all, the denominator equals 0 when x is equal to 2 and what other value? 3. And again, I might not factor it for you on the test, but I'll make it something that's pretty easy to factor if I do. I'm not trying to test, there's going to be some algebra, and there's times where the calculus depends on the algebra, but I don't want to make that the main focus of the test, because this is a calculus class. And then what do you have to be careful of? You got to check now the numerator at 2. 2 times 2 squared is 4. Minus 4 times 2, that's minus 8. You get negative 4 plus 1. You get negative 3. And the numerator at positive 3 is 3 squared is 9 times 2 is 18. Minus 12 is 6 plus 1 is 7.
For n of 2,
Yeah.
I don't think it's negative 3. Because you get 8 minus 8 plus 1.
Oh, oops, it should be 1, right?
Yeah.
Yeah, my bad. Yep. I forgot to multiply the 2 and I plugged the 2 in. Okay. So yeah, d of 2 and d of 3, the denominator at those values is 0, but the numerators are not. So you can say the vertical asymptotes are x equals 2 and x equals 3. Now here's the verifying with a limit part. I'm just going to do one of these. You can do it from the left or the right. You just need to do one-sided limit. One would be enough. You don't have to do both. So let's say I do the left-hand limit as we approach 2 of my function 2x squared minus 4x plus 1 over x minus 2 times x minus 3. Now this is one of those ones where you either have to reason it out or you have to do it numerically, making a table. Okay. Now, I'll tell you a little fact. So, the limit as x approaches a of, let's write it this way, n of x over d of x. This will equal plus or minus infinity whenever, let's do left-hand limit, the limit of the numerator is not equal to 0, but the limit as x approaches a of the denominator does equal 0. So if the limit on top is non-zero, but the limit of the bottom is 0, the limit will always be plus or minus infinity. But I do want you to choose whether it's positive or negative. Okay, so this is plus or minus infinity. I already know that's going to be the case because the top doesn't approach 0, but the bottom does. You just have to choose the plus or the minus. Okay. Anybody vaguely remember how to do this? I'll get back to the exam topics here in a second. So what does the numerator approach as x approaches 2? Well, the numerator is just a polynomial. You just plug it in, and we already saw that the value is 1. Okay. So the numerator approaches 1. The denominator approaches 0, but is, now you just have to, the denominator approaches 0, and as you approach 2 from the left, you just have to know if the sign on this function, you have to determine if it's always positive or always negative. Okay. So here's a number line. Say that's positive 2, we're approaching from the left. You can just pick a test value to test the sign. Pick something like 1.9 or something. Okay. Or think of it like this. The numerator, when you get close enough to 2, since it approaches 1, the numerator is going to be positive eventually. And then if you're approaching 2 from the left, just plug something like 1.9 into the denominator. 1.9 minus 2 is negative. 1.9 minus 3 is negative. So a negative times a negative is positive. So if the top is always positive as you approach 2, but the bottom's always positive as you approach 2, this whole fraction will be positive the whole time. So the limit is positive infinity. So first of all, if the top approaches a non-zero and the bottom approaches 0, the limit's plus or minus infinity. And then you just have to think about what is the sign of this function as we get close to 2 from the left. You can just plug something like 1.9 in and see if it's positive or negative, and that'll determine the sign over here. Okay. And then I think the horizontal asymptotes are actually easier to take the limits of. Okay. Now, and then you could do the same thing at 3. But I think as you approach 3 from the left, I think you're actually going to get negative infinity that time. The top will approach a positive number, and if you plug something like 2.9 into the bottom, this factor will be positive, but that'll be negative. So if you approach 3 from the left, it'll be minus infinity instead. So there's not really a lot of algebra, it's just kind of reasoning it out. Or you have to make a table of values. Now, what are the horizontal asymptotes of f of x? It might be easier to see it if I multiply it back out. The bottom would be x squared minus 5x plus 6. So the horizontal asymptote is, now it's all about the highest power of x on top and bottom. If the highest power of x on top and bottom is the same, the horizontal asymptote will just be the ratio of what? Yep, the leading coefficients on the leading term. The leading coefficient on top is 2. The leading coefficient on the bottom is 1. So the horizontal asymptote will just be the horizontal line y equals 2. And then, I guess it's almost kind of silly to verify that with a limit, because here, though, instead, a horizontal asymptote is something the graph approaches as x gets really large or gets more and more negative. So taking a limit of a function as x approaches infinity, if that equals a finite value, that gives you the horizontal asymptote. Now, what's the main rule at an infinite limit of a rational function? Is it's just, you can throw away all the lower power terms on top and bottom. So you just take the leading term in the numerator over the leading term in the denominator, but 2x squared divided by x squared is always 2, and the limit of a constant is a constant. And that's another reason why the horizontal asymptote is 2. Okay.
Will you have us verify by limits for horizontal asymptotes?
Yeah, I could.
Okay.
We're gonna need we're gonna need to use these ideas of infinite limits later. So I don't know. I think it's good to just make sure we can verify. Okay. part of it too is it gives us practice with knowing how to understand definitions and to verify things through definition. Yeah.
So for the vertical asymptotes,
Uh-huh.
I'm confused how you verify if they come out to two different answers. Cause like when you did 2 from the left, it was positive infinity, but.
Well, and then I did 3 from the, I was talking about doing the limit as x approaches 3 from the left.
But it's this, I'm just confused because it's the same equation. If you're verifying it, how are you getting 2 different answers?
It's about the behavior.
Okay.
Let me kind of sketch a rough draft or a rough sketch of this graph. The horizontal asymptote's going to be at 2, and then the vertical asymptotes are at 2 and 3. And then I already know as you approach 2 from the left, you're really going to positive infinity, so maybe the piece to the left of 2 looks like this. But between 2 and 3, your graph might look something like this. So as I approach 2 from the left, the function goes to infinity, and then I was talking about approaching 3 from the left, and the limit would have been negative infinity. And then you might have something like this again. In fact, I think that's what this graph is going to look like if you had a rough sketch of it, if you went into Desmos and plotted it. Okay. So the limits are just verifying the behavior at the asymptotes. So usually with a vertical asymptote from either side, the function either always goes up or goes down. And that's all these limits are saying. And they'll be useful later on because we're going to use limits and derivatives to sketch graphs of functions. I think that comes up in chapter 4 if I'm not mistaken.
Christy.
Yeah.
So the limit is only to see the behavior part.
Well, it's to verify that you do have an asymptote at x equals 2, and it gives you further information about the behavior close to the asymptote. Yeah. It's giving you 2 pieces of information at once.
So, just for example, if 2 in the numerator, if that was 0, you just wouldn't look at it, right? Because it wouldn't be a vertical asymptote.
If the limit on top was also 0, or?
Yeah.
Yeah, then, so here's a fact too. If the limit of the numerator is 0 and the bottom's also 0, that probably means there's a common factor that you can cancel off. But yeah, if your limit on top and bottom is 0, the limit of the quotient will always be a finite number.
So you just, okay.
Like, I'll give you an example if you want a clarification there. So, I'm just going to give you something factored. If I do the limit as x approaches 4, say you were able to factor and get x minus 4, x plus 5, and in the bottom you get x minus 4 over x plus 2. Now, it's not originally going to be factored. You're going to notice that when you try to plug in 4, you get 0 on the top and bottom. So that means you need to factor top and bottom. And that'll allow you to cancel off a factor. That becomes the limit as x approaches 4 of x plus 5 over x plus 2, and then now what can I do? Yeah, now you just plug 4 in, and you get 9/6.
But, so that's what you meant by, so x equals 4 can't be a vertical asymptote because the top would also equal 4, right?
Exactly. Yep. So if you go back to vertical asymptotes, 4 makes the bottom 0, but it also makes the top 0, so you don't have an asymptote there. What you'd really have is you'd have a hole in the graph. And then negative 2 makes the bottom 0, but not the top. So the only asymptote of this function would be x equals minus 2. And I think the way I've set it up is, I think the horizontal asymptote would be 1. Because the leading term on top is x squared, and the leading term on the bottom is also x squared. Okay. So I don't want to spend all class just doing that because... so yeah, make sure you can find vertical asymptotes and horizontal asymptotes, and then just make sure you do a couple examples, just understanding verifying the definitions. Okay. So for a horizontal asymptote, you take the limit as x goes to infinity and make sure it equals your conjecture or whatever, your guess, using algebra. And then for the vertical asymptotes, you take a limit as you approach your asymptote from the left or right, and you should either get infinity or minus infinity. Okay. All right, so what other topics are there? So I think that basically takes care of chapter 2. Like, we didn't do any limits algebraically yet, Make sure you look at some piecewise functions, because so I could make something up like that too. If I had f of x was x squared minus 3 if x is less than 0, but it's x plus 2 if x is greater than or equal to 0. I could ask you something like, what's the limit as x approaches 0 from the left? At any other place other than 0, like if I wanted the limit as x approaches 1, I just plug 1 into whatever function corresponds to that x value. Right? Like, let me go off to the side and do that first. So if you're taking a limit at a place where you're not breaking it up, what am I going to do here? Sorry. If I'm approaching 1, eventually when we get close enough to 1, is x going to be positive or negative? You're approaching 1, folks. When you get really close to 1, x will be positive. So I replace f of x with x plus 2. And then I just plug in 1 and get 3. Okay. So if you're taking a limit of a piecewise where it's not being broken up, you just need to know which piece to use, and then you just plug in the number. But say I want to know does the limit exist at 0. Okay. So I could have you do a left-hand limit. Okay. And then what would you do in this case? If you approach 0 from the left, thinking of a number line, here's 0, positive numbers go to the right. If we're getting closer and closer from the left, we're talking about negative x values. So which equation would I use in that case? You'd use the top one. And then you can just plug in 0 and get negative 3. Okay. What if you do the limit as x approaches 0 from the right of this piecewise function? Which equation do you use this time? If you're approaching 0 from the right, you're talking about positive values. So I use the x plus 2 this time. And that'll give me 2. So does the original limit exist at 0? That's my question there. Does the limit as x approaches 0 of f of x exist?
No.
No, and what would be the reason why?
Because the left and right hand limits are different.
Yep, because the left and right hand limits are different. Also, another question, would the function be continuous at 0? What was the second condition on your continuity checklist? The limit has to exist to be continuous there. If this limit doesn't exist, is the function continuous at 0? Nope. Okay. So there's lots of variations. We could spend a whole hour just doing limits. Okay. So next thing we need to do is talk about all the derivative stuff you need to know. Okay, so all the limits graphically and analytically, or graphically and algebraically, continuity mainly graphically. You should be able to find vertical and horizontal asymptotes and verify with limits. And then the next piece here, well, what was the next thing we did? Once we learned about limits and how they work, now we started talking about derivatives. So A, you should know the definition of the derivative. And use it to find derivatives. There will be one question where I say use the limit definition to find a derivative. If I don't say what to do, if I just say find the derivative, you can use our rules. Like our power rule, our constant multiple rule. Okay. So anyone want to maybe just do a quick one of these just to kind of see? Typically this is one of the things I think people struggle with a little bit. I noticed that once you get to the rules, I think people really appreciate just how easy the rules make finding derivatives.
Well, it's also a way to check your work after.
Exactly.
Yeah.
So here's one thing you should do. If you have this question, Ollie made a great point. If you see that this question will be on the test, I'll guarantee you. So what you'll do is you'll use the limit definition to find the derivative, and then you can verify your answer by using the rules. You won't get very many points if you don't use the limit definition and you just use the power rule and stuff. I'll maybe give you like half a point out of 4. Okay, so here's an example of this. Let's find f prime of x if f of x equals, I don't know, polynomials are easy, but let's do 1 over t squared plus 1. I'm doing a more challenging one on purpose. And I should make sure I say this, using the definition. Okay, so the definition, f prime of x, it's the limit, and what goes under the limit?
Of h approaches
Okay,
0.
it's always as h approaches 0. That's the saying your increments are getting smaller and smaller. And it's the limit as h goes to 0 of the, starts with a d, difference quotient. Yep. And the difference quotient is f of x plus h minus, oh, what did I do that was kind of silly here? Let's not use t, let's use x. I can use t's, but I have to make sure I'm consistent with all my variables. I did see a few people do that sometimes on the homework. Sometimes there'd be, some people would have a mixture of different variables like x and t's. If you have a function of t, all the variable, other than h, all the variables should be t's. Okay. And then now you'll do the limit as h goes to 0. I wonder if this one will be even fair to do. I gotta think for a second.
It's difficult to find a common denominator. You have to.
Yeah.
I don't think we can do this one yet.
Well, you can multiply out the denominator and then find a common denominator.
Yeah,
It's
but
just kind of a
I think it's
pain.
going to
Yeah.
algebraically be a nightmare. Okay, I'm not going to put something on the test that's completely a nightmare. But how about I do this? Let's just switch it to 1 over x squared. Is that all right? Yeah, that'll be much nicer. Okay. So in the numerator now, you get 1 over x plus h squared minus 1 over x squared. Still everything divided by h. And now you have a complex fraction that you have to simplify. Now, f of x is really x to the minus 2, right? I'm going to do this first, because I'm going to write down what our answer should be before we get there. So using the rules, f prime of x is just minus 2x to the minus 3. Or, if you rewrite it, minus 2 over x cubed. Yeah?
When we're doing the definition, can we pull aside and do the algebra? Or
Yeah.
do you want us to do it?
You can do it either way. You can do equals and carry the limit and do the algebra as you go. Or we could extract this, which I'll do that anyways. Let's come off to the side and do the algebra, because sometimes it's a pain to keep writing equals limit, equals limit, equals limit. So let's do all the algebra simplification all at once, so we don't have to do that. I like that idea. Okay, so what do you want to do in the numerator first? Okay, so you could get a common denominator. Anybody want to maybe see a different method? Just to see if you, I mean, there's another way to simplify complex fractions.
Could you move it up instead of?
Like, just multiply by 1 over h up here.
Well, yeah.
Yeah, you could move it up, but really what I mean is you could get the common denominator and combine fractions, and then instead of dividing by h, multiply by 1 over. Here's the other trick.
We're just gonna use
You multiply on top and bottom, so I'm multiplying the main fraction, and I'm going to multiply by something that cancels this denominator and this denominator at the same time. And that would be the product, x squared times x plus h squared. And then I also have to multiply h on the bottom by that. I didn't show you this in class, but I figured this would be a good way to do it. Now, this is really in parentheses, so you can take the first term times x squared times x plus h squared. And what's going to cancel if you do that? This denominator will cancel with the x plus h squared. So you're just left with x squared right there. And then what happens if you take 1 over x squared times this?
The x squared would cancel.
The x squareds will cancel, and you'll get minus x plus h squared. And in the bottom, you'll have x squared, x plus h squared times h. Because I'm just multiplying all three of these. Now, if you do the get a common denominator route, you'll have to do 2 or 3 extra steps. Okay, so all I did right here is I multiplied by something that clears both denominators, and then it got distributed through. If you do the common denominator route, I'm just going to show you get the same thing, if I can do this quick. So say I do common denominators. So that this way would be I'd multiply this fraction by x squared over x squared, right? And I'd multiply this fraction by x plus h squared over x plus h squared. Okay, so I get x squared over x squared x plus h squared minus x plus h squared over x squared x plus h squared. And then you combine to a single fraction, that's what the numerator becomes if you get the common denominator. But instead of dividing by h, I can multiply the top fraction by, and then do you get the same thing anyways? Okay, so there's really 2 methods. There's the get the common denominator method. That'll work just fine. If you're comfortable with that, stick with it. Okay, it might not be worth it to try and learn a new method. But the other thing that works is take your main fraction and multiply by something on top and bottom to cancel both denominators at the same time. Okay, so I just wanted to show everybody that. You can choose which way you like to do it. And then now, from this step, what do I have to do up top? We can't distribute the negative
You
yet.
have to multiply that, right?
Yeah, we'll have to FOIL the x plus h squared. So you get x squared minus x squared plus 2xh plus h squared. Remember, the middle term is always just twice the product of x and h. And then now what I can do with this, oh, let me let you caught up for a second. And then now what can you do with the negative?
Distributed.
So when you just, you'll distribute it. Notice the x squared minus x squared will cancel. So you just have to distribute the negative to the second 2 terms. So you get minus 2xh minus h squared over x squared x plus h times h. And then finally, you can cancel 1h from top on the top and cancel off with this h in the bottom. So you get
H squared. X plus h squared.
x plus h squared, thank you. So after you cancel out an h, you get minus 2x minus h over x squared, x plus h squared. Okay, so now I can replace that back. Once you've canceled that h, that means you're ready to take the limit. So I factored an h out of the numerator and canceled it with the 1 in the bottom. And then now I can just plug in 0. You're going to get minus 2x over x to the 4th. And then when you cancel an x from top and bottom, you get minus 2 over x cubed. Okay. That one's kind of messy. We'll see how nice I want to be on the test. Most of you might be just hoping that I give you like an x squared plus 2 or something like that. Okay. It will not be linear though, because that's almost too easy. If I'm nice on this question, I gotta be mean somewhere else. But I won't be completely mean all the time. Okay, So that's the limit definition. How much more of a pain in the butt is that than just using the power rule? How long did that take me? What, 5 seconds? This took us what, like 5-10 minutes? Okay. So limits from definition, and then the next is going to be, derivatives from definition, and then you can know the derivative rules and how to use them. So know your power rule, your constant multiple rule. Know that the derivative of a sum is the derivative of each term. Okay. And then make sure you know your exponential derivatives. The derivative of e to the x is? That's the easy one. Okay. And then you have to be careful with the others. Anybody want to do one real quick? We got a mixture. I'm going to do a mixture of powers of x and exponential.
Certainly couldn't hurt.
Certainly couldn't hurt. And then after we do this, the only thing left is the marginal analysis in the business applications. Okay. So let's say f of x, let me grab something that works. Let's say f of x is x squared times 1 minus x plus 3 times, I don't know, I'll do 1/2 to the x power plus 2 over e to the minus x. Now, you might have to do some algebra before you can even take the derivative. Okay, there's certain derivative rules we don't have yet. In fact, on Tuesday after the exam, we're going to learn the product rule and quotient rule. How do you take derivatives of products of functions or quotients of functions? Okay, so first of all, here's a product of two functions. We don't have a rule that tells us how to take that derivative. So what do I have to do with that x squared? Multiply through. So that'll become x squared minus x cubed. So I'm not even taking the derivative yet, we're just simplifying algebraically. The middle term is okay, because that's just a base to the x power with a constant out front. I think we can find the derivative of that. And then what do I actually have to do to take the derivative of the third term? That's a fraction or a quotient, and I don't know how to take derivatives yet.
You just switch the power over.
Okay, yep. Instead of dividing by an exponential with a negative exponent, you can take 2 and multiply by e to the x. So you move it up into the numerator by changing the power from negative to positive. Okay, so that's still f of x. And then from here, let me remind you of a couple rules. So your main rules, essentially, d over dx of x to a power is going to be n x to the n minus 1. We don't know how to do this yet, though, if n is negative 1. Or actually, we would have. I just didn't tell you. Actually, that's a lie. We know how to do that. Chris. Thinking about integration, I got a little bit ahead of myself. So there's power rule. You've got the constant multiple rule, which means if you have the derivative of a constant times a function, you just take the constant times the derivative. The derivative of e to the x we saw as just e to the x. And then who remembers this one? General base.
So it's b to the x, natural log of b.
Okay, that's going to be natural log of the base times b to the x. Okay. And then there's the one rule too that tells you if you take the derivative of a sum of functions, you can take the derivative one at a time or term by term. Okay, so f prime of x, derivative of x squared is 2x. Power comes out front, you reduce the power by 1. Derivative of negative x cubed is minus 3x squared plus
3 ln 1/2 times 1/2 to the power of 9.
So the middle term, it's the constant times the derivative of 1/2 to the x, which will be natural log of the base times the same function, plus, and then does the derivative of the last term become different? Or is it still going to be 2e to the x? Yeah, because you take the constant 2 times the derivative of e to the x, and you get 2e to the x. So there's your derivative. Try doing that one with the definition. That would be an absolute nightmare. I don't even know if you could do the algebra to do it. Okay, some of these functions are almost impossible to use the definition with. So I'm very limited with what kind of things I can ask you about.